Hello, my name is Medet, and I'm a research assistant at the Institute of Smart Systems and Artificial Intelligence. And today, I'm introducing one model to rule them all, a universal transformer for biometric matching. Let me start with explaining what biometric matching is. Biometric matching is the process of verifying a person's identity based on the person's unique biological or behavioral features. These features include facial images, voice recordings, fingerprints, and others. In this work, we introduced the first system that's trained on three modalities: audio recordings, visual, and thermal facial images. It is also input agnostic, meaning it can accept any of the three available modalities, and third, it can perform any multimodal verification scenario, including unimodal, multimodal, cross-modal, and when it misses a modality. The figure you see showcases the main components of our approach. Our model consists of two major parts: the encoder, which is based on the visual transformer, and the training loss. I'll first go through the encoder, which converts the input data into embedding vectors. And then I will explain how we adapted the prototypical network loss for our multimodal task. As per requirement of the original loss, a training batch is partitioned into query and support sets for every speaker. Because the VAT encoder expects input in an image format, we translate the raw audio data into log-mail spectrograms. The deployment of the single VAT-based encoder with shared weights across all modalities enables us to build a modality-agnostic system. This is the first of a kind approach to deal with the multimodal data, as the previous attempts were limited to using separate encoders or networks for each case. The second important component is the multimodal prototypical network loss. The prototypical network loss centers the embeddings of some class K around a single prototype. The prototype is the representative of a class. Because our task focuses on handling the multimodal data, we introduce a novel approach called the multimodal prototypical network loss. Since we want our model to execute all possible multimodal matching scenarios, our training objective aggregates individual prototypical network losses corresponding to each of those cases. The final loss aims to tightly cluster the embeddings of some class K in a shared embedding space across all modalities. The word shared embedding space here is very important, as it allows our model to manipulate between the embeddings of distant modalities. Let's move on to the evaluation protocol of our model. We provide the test data in the form of pairs of multimodal inputs. Some pairs are positive, meaning both input samples belong to the same person, while others are negative, as the samples are of different people. Then we compute the cosine similarity score between the extracted embedding vectors. We use these values to assess the model's performance. The model performance is then evaluated using a metric called equal error rate, which is used often in biometric verification tasks. We provide our system with multimodal samples belonging to two speakers, which we label as ID1 and ID2. The evaluation procedure consists of the following four scenarios. The first one is the unimodal case, in which both ID1 and ID2 contain a sample of the same modality. In this example, the model is evaluated on the visual data only. Next up is the multimodal case, in which each person is represented with the same set of modalities. In this particular bimodal case, both visual and audio data are available for each speaker. So 9 possible evaluation scenarios are possible as depicted on this diagram. The cross-modal is by far the most difficult one. Here, the model has to deal with sets of modalities that are different from one another. In this illustration, the visual image gets compared to an audio recording. The last but not least is the missing modality scenario. As the name suggests, in this case, some modality is missing. In this figure, the audio modality is the one that's absent. Considering the evaluation scenarios outlined earlier, we trained and tested our model using the speaking faces and voxelab datasets. We start with reporting the unimodal and bimodal results of the models trained on the speaking faces dataset. The uniqueness of the speaking faces dataset is the alignment of audio-visual information along with thermal data. Each cell contains equal error rate for the validation and test splits displayed on the top and bottom rows. The reported values represent the mean results from repeated experiments. Part A shows the results for unimodal models. Parts B to D include evaluations for cross-modal and multimodal pairs. In these parts, the modalities on the horizontal axis correspond to the given modalities of person 1, while those on the vertical axis correspond to the given modalities of person ID2. The darker the shade of the cells, the lower the equal error rate, indicating better performance. This slide highlights that the joint training of two modalities, say visual audio or visual thermal, yielded improvements in unimodal evaluation scenarios compared to the models trained only on one modality. For instance, the visual thermal model performs better in the visual-only evaluation as opposed to unimodal model trained on visual data. Similar phenomena can be observed in the audio-visual case. A similar trend can be seen when comparing the visual thermal and audio thermal models with the unimodal one that's trained on thermal data. Overall, training a model on two modalities improves performance in unimodal evaluations. When we train both audio and thermal modalities, we achieve significantly better performance in audio thermal evaluation scenario compared to using either modality alone. This joint training approach results in a lower equal error rate, demonstrating a superiority over unimodal training with just audio or just thermal data. The main highlight of our experiment is that it's enough to train a single trimodal model instead of 7 individual models for each modality combination. The trimodal results effectively contain all possible evaluation scenarios, such that the scores are comparable with the 6 models presented prior. The fusion of 3 modalities surpasses all other 48 configurations on the test set. Now let's move on to the VoxSelect results. Our audio-visual model performs exceptionally well when compared with other works that are capable of both unimodal and cross-modal evaluation. In single modality scenarios, our bimodal approach outperforms others with the lowest equal error rate. Cross-modal verification is particularly difficult due to the inherent differences in data representation and feature extraction across modalities, such as visual and auditory data. In this scenario, our audio-visual system surpasses other state-of-the-art models, demonstrating that our model effectively handles the sophisticated alignment of the two modalities. Thank you for your attention. Goodbye.